Exercise 7.7 wants you to predict the product and also draw the mechanism for an SN2 process. So the first step is just to draw the reagents. So they give you the names of reagents and just to draw them and to realize what role they'll be playing. So let's try to draw this S2-chloropentane. The backbone is pentane. The prefix is pent, so that means we have 5 carbons. So 1, 2, 3, 4, 5. Now I'm drawing the molecule, so I could number it however I like. I'm going to number it left to right. Excuse me. On carbon number 2, we will have a chlorine. But notice that if a chlorine attaches to carbon number 2, it creates a chiral center. You have a methyl group to the left, you'll have the chlorine, you'll have this propyl group to the right, and then you'll also have a hydrogen bonded to that carbon number 2. So carbon number 2 is going to be bonded to 4 different things. And so it's chiral if we have a chlorine there. Oops. So we have to figure out, we have to make sure that we draw it so that the chirality of that center is a left-handed center. So let's assign priorities. The chlorine has the highest atomic number, and so it's going to get the highest priority, a priority of 1. The hydrogen has the lowest atomic number, and so it's going to get the lowest priority, a priority of 4. The 2 carbons tie, so we make a table. This carbon on the left, going away from the chiral center, is bonded to 3 hydrogens. The carbon on the right, going away from the chiral center, is bonded to carbon and 2 hydrogens. So if you compare this first, just this top row, you'll see that the carbon wins, and so this branch on the right has a higher priority than the branch on the left. So that's the first step in assigning, in drawing a chiral center, is to assign the priorities to the different groups. And now let's just see. We don't know whether the chlorine should be coming out at us or going away. Let's just try one. What if the hydrogen is going away and the chlorine is coming out at us? Would we get an S configuration? Well, you'd go from 1 to 2 to 3. You'd be going clockwise, and so that would be R. So that does not give us an S configuration. So those bonds cannot be that way. They must have the opposite 3-dimensional arrangement. Chlorine must be going away, and the hydrogen must be coming out at us. In that case, do we have an S chiral center? Well, let's see. We go from 1 to 2 to 3, so it's clockwise, and you would think it would be R, but 4 is coming out at us, so you switch it, and it's actually S. And so that does give us our S chiral center, our left-handed chiral center, which is what we wanted. So we know that the chlorine must be going away. So that's S2-chloropentane. I'm going to get rid of the hydrogen for now. That's our substrate. The other character we have in this drama is this sodium sulfide, NaSH. And what you should notice there is that you have a sodium, you have a metal. Anytime you have a metal, metals have really low electronegativity. They give their electrons away to whatever they're bonded to, so in this case, the sulfur. And so the sulfur has a full negative charge and ends up acting as an awesome nucleophile. The sodium is really big. Atoms increase as you go to the left and down on the periodic table. Sodium's all the way on the left. And so it stabilizes that positive charge in a similar way as halogens stabilize a negative charge. Spreads it out over a huge area, so it's really stable. So this is not very reactive, and it floats off into solution. Okay, so we have our nucleophile and our substrate. Now, if you want to see it better, you could see that the chlorine is very electronegative, so it's going to be slightly negative, and because it's stealing electrons from the carbon that it's bonded to, which is slightly positive. So you could see how the nucleophile is going to attack that electrophilic carbon. There's our nucleophilic attack. We knew that was coming because we have an SN2 reaction. In substitution reactions, you always have nucleophilic attack and loss of a leaving group. Now, because it's saying that it's SN2, the nucleophile attacks at the same time that the leaving group leaves. The halogens, if you have a halogen, the halogen is always the leaving group. If you have a halogen on a carbon chain. So we know that we're going to have this 5-carbon chain still. Excuse me. The chlorine will no longer be on it. It'll be living its best life. So we have that chlorine floating off into space. And instead of it, you will have the SH there. But what type of a bond should we draw going to the SH? Should it be dashes? Should it be a solid line? A regular line? Or should it be a solid wedge? Which one should it be? And that's where you'll want to refer back to our discussion in the video on understanding substitution reactions. We drew out this table, and we saw that this, in the case of SN2 reactions, if you have a chiral center, the chiral center is inverted. The leaving group is very, very big. So chlorine is very, very big. So this nucleophile isn't able to attack on the same side that the leaving group is pointing on. So this nucleophile can't attack on the away from us. It has to attack coming towards us. That's the only space that has room. And so you get inversion of configuration. The bond before was going away, and the bond that replaces it is coming out at us. Inversion of configuration. And that's the only product you get. With an SN2 reaction, you only get one product. It's the inversion of configuration product. And so that is the whole mechanism and the product for this reaction. The mechanism is drawn on the left side, and the product is drawn on the right. So let's go through that same process again with slightly different molecules. The first step is just to draw the reagents. So let's draw our 3-iodohexane. Now the backbone, the parent chain, is this hexane. The prefix is hex, so we have 1, 2, 3, 4, 5, 6 carbons. Now I'm drawing this molecule, so I get to number it however I want. I'm going to number it left to right. On carbon number 3, we're going to have an iodine. So an iodine is going to be attached to carbon number 3. But notice that if an iodine is attached to carbon number 3, that creates a chiral center. If we're looking at carbon number 3. To the left, you have an ethyl group. To the right, you have a propyl group. You have the iodine. And then, as the fourth thing, you have hydrogen. So that carbon is going to be bonded to 4 different things. So it's going to be a chiral center, which means we have to draw in the correct stereochemistry. Now the name gives it to us. We want this chiral center to be R, or right-handed. So let's assign priorities and see how we can get a right-handed chiral center. Here, iodine has the highest atomic number, so that gets a priority of 1, and hydrogen has the lowest atomic number, so that gets a priority of 4. The 2 carbons tie, so we make a table. Going away from the chiral center, this carbon on the right is bonded to 2 hydrogens and a carbon. Put those in descending atomic number. The carbon on the left is bonded to a carbon and 2 hydrogens. Put those in descending atomic number. The top row ties, the second row ties, the third row ties. When they tie, you go to the next atom. So now we're comparing this one and this one. And we're going to compare these with a table. The carbon on the right is bonded to a carbon and 2 hydrogens. The carbon on the left is bonded to 3 hydrogens. And remember, we're always going away from the chiral center. So if you compare that top row there, you'll see that the carbon on the right has the carbon. And so this branch is a higher priority than the branch on the other side. So we have our priorities. Now let's just try something. Let's just say, what if hydrogen's going away? Let's just try that. If that doesn't work, then we'll switch it. But what if hydrogen's going away? Does that give us R? Well, you'd go from 1 to 2 to 3. That's counterclockwise, so you'd think it would be S. 4 is pointing away, so that would be S. Well, that's not what we want. We want R. Okay, so then we'll switch these. Instead of hydrogen going away and iodine coming out at us, hydrogen will be coming out at us, and iodine will be going away. So now if you go from 1 to 2 to 3, it's still counterclockwise. You would think it would be S, but 4 is coming out at us. So we switch it, and it's actually R. So this, having that arrangement gives us the R. So this is the correct drawing for R3 iodohexane. Okay, so this is our molecule. I'm going to just leave the leaving group on there. Take the hydrogen away so it's not distracting. Now let's look at this NaCl. Now that's table salt. But a similar thing happens with this as happened with NaSH. This is a metal, so it has very low electronegativity. It gives its electrons away to the thing it's bonded to, the chlorine, which has very high electronegativity. So really this is Na plus and Cl minus. Now, when you put these into solution, they come apart. And the sodium is a very large atom, so it dilutes its positive charge over a big space, and it's very stable. The chlorine, though, is relatively small, and it has that full negative charge, so it's in a lot of lone pairs, so it's unstable. That's our nucleophile. How will that attack the molecule? Iodine is at the far right of the periodic table. It's pretty electronegative, steals electrons for itself, becomes slightly negative. The carbon it's bonded to loses those electrons and becomes slightly positive. Our nucleophile, chlorine, swoops in, attacks the electrophile. So that's nucleophilic attack. And because all of these are SN2 reactions, we're going to get loss of a leaving group at the same time. So we have nucleophilic attack and then also loss of a leaving group. Those two happen at the same time. So now in our product, we're still going to have those 6 carbons. And on carbon number 3, we won't have the iodine anymore. That'll be off, living its best life. Very large atom, so it's going to be able to stabilize that negative charge. Who knows what adventures it'll run into? Maybe it'll stick together with the sodium for a little while. Maybe it'll just be surrounded by water for the rest of its life. Instead of the iodine there, we'll have the chlorine. And the question is, what type of a bond do we need to put here? Should it be a dashed line? Should it be a straight line? Should it be a solid wedge? What type of a bond? And for this, we need to remember that in SN2 reactions, you always get inversion of configuration at a chiral center. This iodine is enormous. That's why it's such a good leaving group. But that means that the chlorine cannot attack on the same side that the iodine's on. It has to attack on the opposite side. So if the iodine is going away from us, chlorine had to attack coming towards us. That's the opposite side of where the iodine was. It's the only side that had space for it to attack. And so this is the product we'd end up getting. You only, for SN2, you only and always get inversion of configuration with the chiral center. So this whole thing is the mechanism on the left and also the product on the right of the reaction between, the SN2 reaction, between R3 iodohexane and sodium chloride. All right, let's do one more of these. So, first step, we'll draw the reagents. Now, R2 bromohexane, that is going to be our substrate. The parent chain is hexane, so we have 1, 2, 3, 4, 5, 6 carbons. I'm drawing this, so I get to number it however I want. I'm going to number it left to right. On carbon number 2, that's where we're going to have our bromine. But if you'll notice, if you put bromine on carbon number 2, that turns carbon number 2 into a chiral center. Because to the left of that, you'll have a methyl group. To the right of it, you'll have a butyl group. On top, you'll have the bromine, but then you'll also have the fourth thing, the hydrogen. That's implied. So you end up having 4 things bonded to that carbon, and so that carbon in carbon number 2 is a chiral center. So we have to draw bonds to the bromine and to the hydrogen that give the right chirality for that atom. And we can see in the name that that chiral center needs to be right-handed, needs to be R. So let's assign priorities. Bromine has the highest atomic number, so it gets a priority of 1. Hydrogen has the lowest atomic number, so it gets a priority of 4. The two carbons tie, so let's make a table. Carbon on the right is bonded to carbon and 2 hydrogens, going away from the chiral center. Carbon on the left is bonded to 3 hydrogens, going away from the chiral center. So you compare these tables one row at a time, and in the top row, you can see that the carbon on the right has a higher priority than the carbon on the left. So now that we have these priorities, we can just draw in a type of bond for the hydrogen and the bromine. We know a tetrahedral atom needs 2 bonds in the plane, 1 bond coming out at you, 1 going away. The 2 bonds in the plane are already drawn. So let's draw the bromine coming out at us and the hydrogen going away. Let's just try that. If that doesn't work, then we'll switch it. Does that give us an R chiral center? Well, you go from 1 to 2 to 3. That's clockwise, so you'd think it would be R. 4 is going away from you, so it is R. We don't switch it. So that is the correct way. If it were incorrect, then we would switch these 2 bonds. We'd have the other coming out and the other going away. But as things are, this is R2-bromohexane. And so I'm going to erase this, erase everything except for that leaving group, which is going to be relevant in our SN2 reaction. Now the other thing here, sodium hydroxide, that is that's going to be our nucleophile here. And we've seen sodium hydroxide before. We've seen it in this previous exercise. We had NaOH, and we saw that that was called sodium hydroxide in that previous exercise. So sodium hydroxide is NaOH. Now we have the metal there, so really this is an ionic compound where the metal has a full positive charge, gave its electrons away to the electronegative atom, the oxygen, which has a full negative charge. Sodium is really big, it's very stable with that positive charge, and it meanders off. The hydroxide is going to come toward here and act as the nucleophile in our reaction. Bromine is electronegative, it's all the way on the right on the periodic table, so it steals electrons for itself, and the carbon it's bonded to loses those electrons and becomes slightly positive. And that makes it attractive to this hydroxide nucleophile. Hydroxide swoops in and attacks the electrophile. That's nucleophilic attack. At the same time, because this is an SN2 reaction, that's what it told us in the prompt, at the same time, we're going to have loss of a leaving group, and so this bromine will take its electrons and pop off of the molecule. So we have nucleophilic attack and loss of a leaving group happening at the same time. That's an SN2 reaction. So we still have all those carbons there. The bromine will have popped off. It'll be living its best life somewhere else in the container. Who knows? Maybe running into the sodium that was in the sodium hydroxide. And instead of bromine on carbon 2, we're going to have our hydroxide on carbon 2. But the question is, what type of bond should we draw to the hydroxide? Should it be a dashed wedge? Should it be a regular line? Or should it be a solid wedge? And that has to do with an SN2 reaction. If you ever have an SN2 reaction, you get inversion at a chiral center, you get inversion of configuration. If the leaving group was pointing in one direction, the nucleophile will be pointing in the opposite direction. You invert the direction of the configuration. Because the leaving groups are good leaving groups because they're so big. They're able to leave and take this gigantic charge because they dilute it by spreading it out over a huge area. So they're really big, so that makes them great leaving groups, but it also means that a nucleophile it's too crowded there for a nucleophile to attack on the same side that the leaving group's on. So if the leaving group is pointing out towards us, there's no room toward us for the nucleophile to attack. So the nucleophile must attack on the opposite side, the side going away from us. So you get inversion of configuration. What starts out as a bond toward us for the leaving group becomes a bond going away from us for the nucleophile. And so this whole thing is going to be the mechanism on the left side and the product on the right side for this SN2 reaction between R2 bromohexane and sodium hydroxide. So in each of these reactions, we drew the reagents. We were careful with the R and S naming. We drew the nucleophilic attack and loss of the leaving group at the same time, and we were careful to show inversion of configuration for each of these SN2 reactions.